Hi, welcome to the next of our series of mini lectures. Today we're going to be talking about transfer functions in optics, and this is something you don't really find in any undergraduate textbooks. There are some graduate textbooks devoted to it in the context of wave optics, but I think it's a very important subject, not because it gives us a lot of equations, but because it gives us a way of thinking about optical systems. So here's the diagram you've seen several times before that breaks the optical system we'll be building down into optical and electronic components, and you see there's overlap between these. And we're really going to be focusing on the optical system today, which for the particular system we're building consists of light coming in to filters, going through a sample, and then being filtered again. Another way that you can draw this system will be shown in a little bit, but let's first get to the idea of what a transfer function is, because any part of a system like this that has an input coming in over here and an output coming over here can be expressed as a transfer function, and we usually in engineering use the term H for that, and H is a common expression. So just to review transfer functions in electrical engineering, this should look very much like one of your signals or systems courses. We have some electronic system we define a frequency-dependent transfer function H for, with an input X and an output Y. Both of these are functions of frequency, and we can relate the input and the output through the transfer function by this expression, and we see the transfer function is just the output divided by the input of the system. And we often express transfer functions of electronic systems, particularly in things like filters, by what's known as a Bode plot, where you sort of extrapolate on a logarithmic scale to straight lines. And we see that in fact there's an amplitude response of the system, or magnitude response if you want to call it that, and also a phase response of electronic systems. And this should definitely ring some bells from your memory, because I think everybody in this class will have seen this before. Let's take another look at the optical system we're going to be building in a little bit more detail, where here we have our light source, we have some kind of light collection optics we haven't drawn yet, the filter, a sample of some type. In this case our sample is going to emit light, light collection system, another filter, then some kind of optical detector. And what we're really interested in doing is thinking about part of this system, basically all of this, as a single black box, as a single system. And in order to draw that a little bit better, I'm going to just basically rotate my diagram so it's linear. And I'm going to say what I care about is the input and output of this system that I represent as a black box. So I have rays of light coming into my black box and rays of light leaving the black box. And there are several ways we can write a transfer function for this. The easiest is just the power transfer, T, where T is a number of the total amount of power we have coming into our optical system, how much power comes out, and if we call this Y and this X, then the power transfer function obviously is just Y over X. That's not so interesting since it's just a number. What we're really concerned about most in this class is thinking about photons traveling in straight lines. You can also represent these as rays of light coming into a system. They have many different colors. And so in this case, our input is a function of wavelength, and our output is a function of wavelength, and our power transfer T, although I think I should call it H, is also a function of wavelength. So we have some kind of curve or formula that describes how the different wavelengths of light go through the system, the power that comes out in different ways. Of course, the photons can come in different directions, as is shown on the top of the screen. So one can also define for an optical system, if you want to, although it's not that important in this project, although it does have some importance, what you might call a directional transfer function. And we know what this is. We've already dealt with this. We redraw our optical system with an input plane and an output plane and define positions and slopes, and we can call this directional transfer function an ABCD matrix, or array matrix of the system. And earlier in the class we already learned how to deal with this. There is, of course, the true description of any optical system that you will use in higher level classes, where essentially the perpendicular to the rays form a phase front, which is shown as this blue line. It goes through a system, and the phase front comes out, and you need a full wave description of light here, because the amplitude or the transfer function in this case has an amplitude component, a phase component, and also a directional component, because you notice our phase front is being distorted as a function of where it comes in. And so it is possible to develop rather detailed mathematics about how to do amplitude and phase transfer functions of optical systems, but that's really a graduate level topic in Fourier optics, and we're going to skip it for now. To give you an idea of the ubiquitousness or the use of optical transfer functions, we can describe any optical system with a transfer function h, where we have photons coming in and photons coming out, but these photons may be going in different directions or have different colors or a different amount of photons corresponding to a different amount of power. The spectrophotometry system we are building in this class is an example of a system where the transfer function is called by a filter, a sample, and another filter. The Internet is an example of another photonic system where the input is a range of wavelengths around 1550 nanometers generated by a laser. These are filtered or selected. Many of these go through an optical fiber and are filtered on the output and are detected and then go to the electronic system, which routes the electronic signal to your computer so you can browse the World Wide Web. Another example is medical imaging or a CAT scan. In this case, instead of visible frequencies, we have gamma rays, very high frequency electromagnetic radiation. It goes through some kind of beam forming and wavelength selection system. It's beamed through a patient, filtered, and goes through the detector. And then in the electronics over here, there's a rather complex algorithm that looks at the transmission as a function of angle and recreates the inside of a human body. You've all seen these images. So this idea of transfer function is very basic to engineering. It's very important to optical systems, and although few textbooks talk about it, it gives us a very powerful set of concepts for thinking about design of optical systems.